welcome back. I'm welcoming you all to this beautiful online learning platform, Unacademy. Now we are happy to announce that our Unacademy is going to providing online training for GATE and engineering service examinations. About myself, I G Venkata. I have 16 plus years of teaching experience. So far I mentored more than 60,000 students for their GATE examination. At present I am pursuing PhD from JNTU Kakinada in VLSI design. First we check how to get Unacademy learning app into our device. Just go to Play Store in your device. Type Unacademy. Then it will show Unacademy learning app like this. Unacademy learning app like this. By clicking on this install button, it will install the Unacademy learning app into your device. Once you open that app, it will show what are the different courses available in that, and in each course what are the different subjects and each subject handled by which educator, which faculty. It will show that information to you. Now here are the top educators, few of the top educators from Unacademy. Tiwari sir, he is the IIT topper. Ankit Goyal sir, he obtained 2 times All India first rank in GATE examination. He was awarded President of India Gold Medal in IIT Indore. Jaspal Singh sir, he is ex-IAS officer. He got All India 4th rank. Sanchit Jain sir, he has more than 8 years of teaching experience and a very sound experience in teaching the students in computer science. And here are few more top educators. Here are few more top educators who are working in Unacademy. Here are the few of the top educators. Now see, engineering service examinations 2021, there is a test series we are going to be conducting. In that 10 questions we provide and 20 minutes of time. Now it was curated by the best educators. All India live ranking is provided if test taken is live. If you are taking a test live, your All India rank is provided to you, and it is designed as per the changing demand for engineering service examinations. And for mechanical, the date is 22nd and 29th, electrical 23rd, 30th, civil 24th and 31st, electronics and communication engineering, it is 25th March, and for general studies it is 26th March. Please note down the dates. Please note down the dates here. For electronics and communication and general studies, 25th March for electronics, and general studies is on 26th. Okay. Now there is a full length mock test available. So in that 150 questions, 180 minutes of time. This is for mechanical engineering, electrical, civil engineering and electronics and communication engineering. The mock test is on 21st and 28th of March at 10 AM. Okay, and don't forget to use my code VRAO10 during subscription to get 10% discount VRAO10. Next, see, so there is a golden opportunity to civil engineering students. Just track the ESC with Jaspal Singh sir. He is the ex-IAS officer. He got All India 4th rank. Now just join us for free test series. There is a free test series. So these are the topics in civil engineering, different topics and the respective date from 6th March to 12th June. Okay, so don't forget, each and everything is going to be very important to this. Okay, join with him and get the more benefit. Now, Ultimate 10 SSC series. So this is for mechanical engineers. 10 questions, 20 minutes of time. 20 minutes of time. Now it is on 1st March, 4th March, 9th March, 12th March and 17th March. Now the timing is at 10 a.m. At 10 a.m. Don't forget to use my code VROW10 during subscription. 10 questions, 20 minutes of time. Okay. Now we move to electrical engineering. In electrical engineering, there are 10 questions, 20 minutes of time. The dates are 5th March, 2nd March, 5th March, 10th March, 15th March and 18th of March. The timing is 10 a.m. Don't forget. Now don't forget to use my code VROW10 during subscription. See, the test can be attempted even after the live test session also. You can attempt this test after live also. You have that option. So my dear students, what you prepared is equal to the what you are going to be attempting. So preparation and writing more number of examinations, both are having equal priority. Both are plays an important role for your examination results. Okay, don't waste your time and attend this series and write the more number of examinations. Get the respective analysis of that exam, and top faculty will come and analyze that paper, explain that paper. Okay, please take a proper note and collect the proper material and get the benefit. Next, now we move to Ultimate 10 series for civil engineering students. 10 questions, 20 minutes. 3rd March, 8th March, 11th March, 16th March, 19th March. The timing is 10 a.m. Okay, don't forget to use my code VROW10 during subscription. Next, GATE or RAID. So now this is a Kickstart Your GATE Preparation 2022. Okay, this is curated by the best educators. All India live ranking is provided. If test series is test is taken in live, if you are writing the test in a live, all India rank is provided to you. It is designed as per the changing demand for GATE. 10 questions, 20 minutes. It is on every Tuesday, Thursday and Saturday 10 a.m. Now use code VROW10 during to unlock this series. To unlock it, use my code VROW10. This is for ME for mechanical, for electrical, computer science and IT, chemical engineering, electronics and communication engineering and civil engineering students. Next, now we are happy to announce that recently we started 2 new batches. For one for GATE 2023, other one is for GATE 2022. Now there is a Ascend batch for GATE 2023 mechanical engineering. This batch was started from 22nd February 2021, and these are the top faculty who are handling the subjects in this batch. For GATE 2022 also the same faculty handling, and it was also started from 22nd February. The same faculty who are handling the subjects in 2023, same faculty are handling the subjects for GATE 2022. Okay. Now there is a Spark batch for GATE 2022 civil engineering students. This is an English batch, only English batches. This batch started from 22nd February 2021. And here are the top faculty who are handling the subjects in this. Now we started a mission DDR for mechanical engineering students. This is for mechanical engineering students. Mission DDR. Okay, for mechanical engineering students. It was started from 22nd February. The top faculty working under this batch is Tiwari sir, Umameshwara sir, Meno Gupta ma'am, Aman Raj sir. Here are the top educators and top faculty who are working under this batch. join this batch and get the more benefit. Now there is a ascend batch for GATE 2023 for civil engineering. This batch was started from 8th February 2021. Here are the top educators who are handling the subjects in this batch. Next, there is a eval batch for GATE 2022. There is a eval batch for GATE 2022. This batch was started from 8th February 2021. Here are the top faculties working under this. The faculty who are handling the subjects of GATE 2023, the same faculty are handling the subjects of GATE 2022. Now we move to eval batch for GATE 2022. Computer Science and Engineering, Computer Science and Information Technology department. Now Ravindra Babu sir, Sanchit Jain sir, Subbarao sir, Mallesham sir, Shweta Kumari ma'am, Vishwadeep sir, top faculty are working under this. This batch was started from 8th February 2021. There is a ascend batch for GATE 2023. This is for electrical engineering. Electrical engineering. This was started from 1st February 2021. Now here are the top faculty who are working under this. Don't forget to use my code VRAW10 for getting 10% discount. So there is a ascend batch for GATE 2023 electrical and electronics and communication engineering. This is the team who are going to handling the subjects in this batch. This batch started from 1st February 2021. Next, there is a eval batch for GATE 2022 electrical engineering. The same faculty who are handling the GATE 2023, the same faculty are handling the subjects here. Same faculty are handling the subjects, and it was started from 1st February 2021. Now for electronics and communication engineering also, there is a eval batch for GATE 2020. This batch was started from 1st February 2021. Now we move to last but not least, chemical engineering department. Now according to my knowledge, throughout India hardly 1 or 2 locations only chemical engineering is available. So my suggestion to these students is, if any of your friends are doing chemical engineering, please inform this one to them, because for them it is very difficult to move from their location to that location where they are providing the training. Now through Unacademy, online training is available. No need to move from their location. Just by staying at their home itself, by their study location itself, they can access that. They can attend the classes by online. They can get the more benefits. This batch was started from 25th January 2020. Even though it was delayed, you don't worry about that. Live sessions they will provide, as well as recorded sessions are there. They will provide that access to that recorded sessions, and they can attend at the same time live sessions also. And if they want any doubts, they will conduct some live sessions. During live sessions they can ask the doubts to the faculty. Okay, don't worry, already 1 month is delayed or 2 months delayed. Don't feel like that. You can provide that benefits. Respect to benefits they will provide. Now just we glance what are the different engineering disciplines available in Unacademy for GATE and engineering service examinations. ECE, electronics and communication engineering, chemical engineering, mechanical engineering, computer science and IT department, instrumentation engineering, electrical engineering, civil engineering, production and industrial engineering. Now there are 2 plans in Unacademy. First one is the plus plan, second one is iconic plan. Plus plan is the basic plan. This is to start your plan in Unacademy. In this plan, India's best educators are going to handle your classes. There are interactive live sessions, structured courses and PDFs are available, live tests and quizzes are there. And in iconic plan, same thing, India's best educators are going to take your classes, interactive live sessions are there, structured courses and PDFs, live tests and series quizzes. Here, by providing a personal coach to you, we will take your GATE and engineering service examination preparation to the next level. Here, what we are doing is we are providing a personal coach. That personal coach is going to analyze the tests and quizzes what you've written, what you attempted. From that, they will analyze where you are strong, where you need more preparation, okay, where you are doing mistakes. That means finally they will verify the gaps in your preparation. They will verify the gaps in their preparation and they will work out to fulfill the gaps in that. That means they, based on the gaps, they will prepare a proper study planner to you and respect to study material to you. Every student, by following these two properly, get success in their examinations. Get success in their examinations. Okay. Now we check the cost for each and everything. Now there is a plus plan. It is available in the form as a 1 month subscription, 3 month subscription, and 6 month subscription, 12 months, 1.5 year, and 2 years. As a faculty, I recommend the students to take minimum of 1 year subscription. Minimum of 1 year subscription. Okay, minimum of 1 year subscription. So the cost for this 1 year subscription is 30,250 rupees. After you, by using my code VRAU10 during subscription, you get it by 27,225 rupees only. Okay, by getting it 27,225 means the cost is more or less close to the amount what you need to spend for traveling if you joined somewhere outside to get the training. Okay, so don't forget, join this and get the benefits more than that what you are getting it outside. Now we are moving to iconic plan. This is the extraordinary plan. Here we are providing a personal coach to you. Okay, it is available in two subscriptions, 1 year subscription and 2 year subscription. For 1 year its cost is 50,250 rupees. Okay, by using code, my code VRAU10 during subscription, you get it by 45,225 rupees. With a 10% discount you get it. Okay, now thank you, thanks for spending your valuable time. Now we are moving to our regular topic. Already rectifiers and filters, already we completed rectifiers, and filters also we started already, and that too there we complete our discussion for what is filter, what types of filters, how we are using filter here, for what purpose we are using filter here. Okay, in rectifiers everything we completed, all those things we completed. Okay, now we go on discuss about the remaining part. See, just I am going to glance what are the things we completed so far. What is filter, and we discuss about this. Types of filters we discuss. Okay, classification of filters, passive filters and active filters. Okay, and how filter is using in rectifiers. Simply for reducing the ripple factor, that means reducing the AC component of the signal, we are going to using the filters. Now so here we define the ripple factor. What is ripple factor we define just, and after that how to calculate that. For half wave rectifier, what is half wave, what is full wave, we discuss here. Output waveforms we get, now that we represented that output waveforms in terms of equations here. Next, types of filters used in rectifiers. Inductive filter, capacitive filter, L section filter, and CLC or pi section filter. These are the filters we are using. So first we take the inductive filter, we analyze that. So this is the output equation, a full wave rectifier, 2Vm by pi minus 4Vm by 3 pi cos 2 omega t. This is the DC component and AC component. This is the representation of that expression we replaced by a constructed by a circuit, inductive filter and resistor, and we analyze this. Now we are moving to second one is capacitive filter. Capacitive filter. Capacitive filter. Okay. What is capacitive filter? Where we are going to be connecting it. Okay. Now, this is our full wave rectifier. First of all, full wave rectifier. It is connected to AC mains. AC mains, and see there at output we have here is output, V output. Now the filter is connected like this. Here is capacitive filter and load RL is connected. Load RL is connected. This is capacitive. Okay, in this output you have AC component and DC component, AC plus DC. Now that AC component is bypassed to ground to this capacitor, and DC component is present at output. This is output V naught. This is V out and this is V naught. Okay, so like that we are going to be analyzing this. Now, first of all, at this point, the waveform what we are getting without capacitive filter. Without capacitive filter. Now for my better understanding purpose, first I am going to getting the output waveform of capacitive filter. Output waveform. From that waveform we are going to be analyzing this. Now the output wave circuit diagram also I am going to use. This is the full wave rectifier circuit diagram. Center tapped bridge rectifier, center tapped full wave rectifier here I am taking. So here is your capacitive filter. And at output we have a load RL. Capacitive filter. See, let us take diode 1 and diode 2. Now the expected output waveform. The expected output waveform is like this. Now this is the expected output waveform. like this. Yeah, this is the expected output waveform. This is Vm. Now see this. Now here I am going to getting output waveform. See this. For positive, okay, from this positive half cycle, once input is a 0 plus, diode D1 is on state. Once D1 is on state, capacitor starts charging. Capacitor starts charging. So capacitor starts charging like this. Charging up to Vm. Capacitor is charging up to Vm. Voltage across capacitor is now Vm. So this is the voltage Vm at capacitor. Now the voltage at this point and at this point, even if you take, that is less than the Vm. Okay, so because of that, both D1 and D2, both the diodes are off state. Once both the diodes are off state, capacitor starts discharge. Capacitor discharging. At this point, when it reaches this point, from this point onwards, D2 is on state and D1 is off state, because D1 is diode 1 facing negative signal, negative half cycle at input, D2 facing positive half cycle at input. But at that positive half cycle, voltage at this point is greater than the voltage at this point, because voltage at capacitor is only this much now. Voltage at this point is greater than this point. So voltage at P terminal of second diode is greater than voltage at N terminal of the diode D2. That means voltage across capacitor. Now again, diode D2 is on state, capacitor starts charge. So already we discussed the operation of this in rectifiers. Now again, now diode is, capacitor is charging. Once capacitor is charging up to here, then both D1 D2 are off state. Now capacitor is both D1 D2 are off state. Now capacitor is discharging. So discharging of capacitor takes like this. This is charging. This is discharging. Now it is capacitor is discharging. So discharge. Again capacitor is charging. Again it is discharging. Charging, discharging, like that. Okay, this is the way we are getting the waveform. Now here, whatever the things here we have, I want to writing its operation. To write the operation of it. So just I am copying that. This now. So I am giving them some time slots. These are the time slots, important time slots. So let us, it is a T1, T2, T3, T4, T5, T6, T7, like that you can extend. Now this is 0. Now I am writing its operation. Operation. First, from 0 to T1, 0 to T1, D1 is on state. D1 is on state and D2 is off state. Capacitor is charging. Second, T1 to T2. T1 to T2. T1 to T2. Both the diodes are off state. T1 and D2. D1 equals to D2 equals to off. Both are off state. Now capacitor is discharging. Capacitor is discharging. Third one, T2 to T3. Here to here. Now this is second cycle. Second cycle means D2 is on, D1 is off. D1 is off and D2 is on. Again capacitor is charging. Capacitor is charging. Next, T3 to T4. Same operation performs. Next, T4 to T5. It is repeats. Next, T5 to T6, like that. Capacitor charging and discharging continues. Now the important thing here is we need to note down is this one. This is one complete cycle here. This is one complete cycle. This is T0. Okay, that is T0. Now that is T0 in this sense. Sorry, this is T0 by 2. Why? Because compared to, I want to compare it with respect to the input signal. Okay, so if you take the input waveform of this is the input waveform of it. This is the input waveform, like this. This is going to be 1 T0 and this is T0 by 2. This is T0 by 2. T0 by 2. Okay, now in the T0 by 2 we have T3 to T4 plus T4 to T5. From T3 to T4 your capacitor is going to be charging. Now let us take it as TC, charging, discharging, TD, discharging interval. It is charging interval. TC, charging interval. Now I am writing that TD is discharging interval, capacitor discharging interval. Discharging interval. And TC is capacitor charging interval or capacitor charging period, interval or period. But if you observe one thing, T0 by 2 is nothing but a TD plus TC. Therefore, TD plus TC is T0 by 2. But from this, discharging interval is much greater than charging interval. So we can write from this, discharging interval is approximately T0 by 2. Discharging interval is approximately T0 by 2. Okay. Now we need to check one thing. Once you know this, whatever the amount of charge, see one more thing. This is Vm, and let us take this is a Vm minus V gamma. V gamma is I am taking, let us a peak to peak value of this. Peak to peak value is V gamma. V gamma. Okay. Now it seems to be a triangular wave. I want to calculate RMS value of this. So RMS value of this one is RMS value of AC component by DC component. Before going to that, the amount of charge it gains during charging is equal to the amount of charge it lost during discharge. Whatever the charge it gained during charging is equals to the amount of charge it lost during discharge. Now I am going to writing that. Now the amount of charge gained by the capacitor during charging equals to QC charging is equals to C into V gamma, because it is going to be voltage is increasing from Vm minus V gamma to Vm. Next, the amount of charge lost by the capacitor during discharge is equals to QD is capacitor discharging is I into T, that means IDC into T discharging interval, but this is equals to IDC into DC current into, it is nothing but T naught by 2, just before we derived it, but T naught is nothing but a F naught, so IDC by 2 F naught, IDC by 2 F naught. Now see this, but the amount of charge what it gained is equals to the amount of charge what it lost. Okay, so just I am going to be adding that. Therefore QC is equals to QD. Sir, here I will show once again what is F naught. Sir, this is your input signal what I am applying at input side. This is the input signal what we have. So this is going to be one frequency, one time slot T naught. Okay, and its frequency F naught is 1 by T naught. That is, so amount of charge equals to amount of discharge. So from that, C into V gamma equals to QD is IDC by 2F naught. So these are the two basic equations of Q. We know Q is equals to CV and Q equals to IT. Just I applied that, not more than that. And one more thing, Here capacity is discharging. During discharging, the current is IDC because the DC current is flowing through RL. Now, so this is the equation for finally. So C into V gamma is IDC by 2F0. So now I am writing from this V gamma value is IDC by 2F0 into C. Now we need ripple factor. So ripple factor of triangular waveform is, first get the RMS value of that. RMS value of triangular wave is let us take a triangular wave like this. We have a triangular wave like this. Like this. This is the peak to peak value of this. This is a peak to peak value. This is a V peak to peak. This is a V peak to peak. So its RMS value of triangular wave is V peak to peak by √3. Just a minute. Okay, next we take this. It is V peak by √3. V peak by √3. This is peak to peak. We need to get peak value. So V peak value is V peak to peak by 2. By 2. That means, for example, this is the well-known waveform plus Vm minus Vm. It is Vm, it is minus Vm. Now the peak value of this one is Vm. How we get that? Vm minus of minus Vm by 2. See this. Its peak value is Vm minus Vm by 2. That is the peak value of this. Same thing here I am doing. Peak to peak by 2. So peak to peak value of this one is, therefore V peak is peak to peak value. We know that. We mentioned it is a Vm and this is a Vm minus V gamma. That's it. So it is a Vm minus of Vm minus V gamma by 2. That is V gamma by 2. Therefore, RMS value of triangular wave V dash RMS. V dash RMS is V peak by √3. So V peak is V gamma by 2 by √3. That is V gamma by 2 √3. Now we know the value of V gamma. Just take that, substitute here. So V dash RMS, we got it as V gamma by 2 root 3. And we know V gamma value is IDC by 2F0 into C. 2F0 into C. Simplify that. Therefore, V dash RMS equals to IDC by 2 root 3 into 2F0 C. Okay, now this IDC by 4 root 3 into F0 into C. And we know one more thing, IDC is equals to VDC by RL. Substitute that one here. For V dash RMS equals to IDC is a VDC by RL into 4 root 3 into F0 into C. Okay, now we need ripple factor. Therefore, ripple factor is RMS value of AC component by VDC equals to 1 by 4 root 3 into here 4 root 3 into F0 into CRL. This is the ripple factor. The capacitor filter. Now here we observed one thing. Ripple factor is inversely proportional to load RL. So if load is changing, ripple factor also changes. This is the drawback what we observed in capacitor filter. To solve this problem, we are moving to L section filter. Now I am moving to L section filter. One is L section filter. L section filter. Okay. Now, so first I am writing as usual full wave rectifier with filter section. Full wave rectifier. This is connected to AC mains. Here is output. Now filter section. L section filter is inductor followed by a capacitor. Both L and C are combined. That is the L section filter. It is load RL. You are taking the output. DC output you get. It is L, it is C. This is the L section filter. L section filter. Okay, and we know that at this output we have AC component plus DC component, and we know the equation for V output. V output is 2 Vm by pi minus 4 Vm by 3 pi into cos 2 omega t. Omega or omega not, as you wish, it's not an issue. This is the equation. I'm going to representing this one by a circuit. Previously, the way how we inductive filter we analyze, the same procedure I'm going to be following. This is our expression, V output 2 Vm by pi minus 4 Vm by 3 pi into cos 2 omega t. First I am writing the circuit. This is 2 Vm by pi. It is minus 4 Vm by 3 pi into cos 2 omega t. Here I am connecting filter section. And connecting a load at out. And one more important thing you need to be consider here is, let us take this is a A, is the point B, it is the ground. Here also you have a ground. This is RL. Now first assumption, for better operation XC reactance of the capacitor should be much less than RL, much less than RL, and XL is much greater than RL. These are the two important things you need to be considered. Now let us, I am calculating the impedance between B to G and A to G. Let Z B into BG is impedance between this one and this one, B to G. Both are parallel. That means now we can write it as RL plus J into XC. Magnitude of B into G is square root of RL square plus XC square. Sorry sir, both are parallel it is. I'm very sorry. Sorry, B and G both are parallel. So RL parallel with JXC. In parallel combination, smallest value is XC. So you get it as mod BG is approximately XC. So the impedance between B to G is XC. Next, I am going to taking this similar way, impedance between A to G is, now this one and this one are series. That means XL JXL plus ZB. Okay, now this is the impedance between A to G. So this is XC. Compared to XC, it is much greater. XL is much greater. Therefore, XL is much greater than XC. So because of that, impedance between A to G is, magnitude of that is simply XL. These are the few assumptions you need to be considered before going to analyzing this filter effectively. Okay, because these assumptions are very important. Why? Because by taking the inductor high value, high reactance takes place. Once high reactance is there, most of the AC component drop across this. If any AC component coming this side, due to this is the parallel circuit, parallel part. Now due to low reactance of this capacitor compared to RL, now that AC component of current is flowing into this. You may ask one thing, sir, this is fine for AC, what about DC? Okay, what about DC? Now first we go and check that also. Now I am writing DC equivalent, DC circuit. See this, for a DC circuit, inductor is open, XL is 0 for a DC, XC is infinity. So that means inductor is short circuit, and capacitor is open circuit. Capacitor is open circuit. Okay, now I am going to writing its equivalent DC. 2 Vm by pi inductor is short circuited, capacitor is open circuited. Here is your load RL. This is the current IDC. Now IDC is 2 Vm by pi RL, and from this DC voltage VDC is 2 Vm by pi. This is the DC component. Okay, that is the DC component, VDC. Now, so for better understanding purpose, I am going to copying the circuit. This how it gives AC current. This AC component is going to provide AC current. So now I am taking AC circuit. AC circuit. For AC, I am taking this is a 0, only AC current. So it is VAC component. It is minus 4 Vm by 3 pi into cos 2 omega t. This is ZAG. This is the AC current, IAC component. Now IAC is VAC by ZAG, impedance between A to G. Now AC component is minus 4 Vm by 3 pi into cos 2 omega t by impedance between A to G, just before we calculated it is, that is XC or XL, that is. This is the IAC value. Now from this we need IAC peak value. So IAC peak. So IAC peak is 4 Vm by 3 pi into XL. That is the value of IAC peak, because RMS value of this current we need. See this. Now I am going to take this. See, this is the filter we have. Once AC current is coming like this, IAC is coming. This is L and capacitor RL. Both are in series. Here voltage division takes place. Now this AC component is coming like this and it is flowing through the capacitor. My intention is I want to calculate the RMS value of output voltage. It is V out. I want its RMS value. RMS value of V naught. I am representing it as, let us take V dash RMS. V dash RMS is nothing but A. This is V and this is G, we mentioned already. This is A and G. This is AC current. Okay, it is coming like this. This is AC current. It is B and it is G. This is AC current. ZBG. This is V output. Now V output is written as V naught is IAC into impedance between BG. Therefore, we know the IAC component value. IAC value. Now we need RMS value of this. Therefore, V dash RMS is V naught peak value by root 2 because it is a sinusoidal signal. Now V naught peak is nothing but a IAC peak into mod impedance between B to G. I am writing, substituting this value, AC into between B to G we have XC. To G we have XC by root 2. We need IAC peak value. Just before we mentioned IAC peak value, 4 Vm by 3 pi XL. V dash RMS is 4 Vm by 3 pi XL. Here it is XC by root 2. Now from this I am going to writing the ripple factor. See this V dash RMS, and we know VDC value is 2 Vm by pi. Okay, now V dash RMS is 2 Vm by pi into 2 Vm by pi. So 2 is there. 2 by 3 into XC by XL into 1 by root 2. This one cancelled, became root 2. Now it is VDC. Therefore, V dash RMS value is VDC into root 2 by 3 into XC by XL. Now take this one this side. Therefore, V dash RMS by VDC equals to root 2 by 3 into mod XC by XL. This is the ripple factor of a L section filter. Okay. Now Here it is independent of RL. Advantage is independent of RL. It is independent of RL. That is the advantage of this. Okay. Just take a note of this equation. This equation is it is very important. Just make a note of this. Okay, now here we are going to, I'm going to defining few things in this expression. Whatever the expression we got here is, in this expression we mentioned some IAC peak value. Just I am going to take that IAC peak value is a 4 Vm by 3 pi XL. That is the IAC peak value, 4 Vm by 3 pi XL. So IAC peak value is 4 Vm by 3 pi into XL. And we know the XL value. XL is 2 omega L. Substituting this, 4 Vm by 3 pi into 2 omega L. It became 2 Vm by 3 pi into omega. Okay. Now here I am going to defining one point, that is a critical inductance. We have one term, critical inductance. LC, critical inductance is LC. It is the value of inductance at which IAC peak value is equals to the IDC. It is the value of inductor at which IAC peak value equals to IDC. This is the IAC peak value, 2m by pi 3 pi into omega into L, critical inductance L C. L became LC because we are taking the value at IAC peak we are making equal to IDC. That means that is the value of critical inductance. L became LC is equals to DC current. We know that 2 Vm by pi RL, critical inductance. Already we derived IDC value. Now just simplify this. Now it is pi gets cancelled, 2 Vm. Now from this LC is critical inductance, LC is RL by 3 omega. This is the critical inductance. Okay, this is the critical inductance value. Okay, now here our intention is always to get a DC component greater than AC component. That is our intention. So if L value is less than critical inductance, then IDC component is going to less than IAC peak value. And if L value is greater than critical inductance, IDC component is greater than IAC peak value. This is the required thing. Always we need to maintain IDC greater than IADC greater than IAC peak value. Always we need DC component more. That is our intention. Our intention is to convert AC signal to DC signal. So goes on, DC component has to increase and AC component has to decrease. That is our intention here. Okay, now, so this is the required condition all time. L value is always greater than LC. So the minimum value of L you have to take is critical inductance. Minimum value you have to take is critical inductance. Okay, now next one. Now at the same time, for example, okay, now I'm writing the critical inductance value. LC is RL by 3 omega. RL by load by 3 omega. For example, some problem taken place in the inductor. This is the filter we have. Now I am connecting the load RL. This is the load RL. See carefully. I connected load RL in breadboard like this. Now what is the difference? Please observe the circuit cleanly. Please observe the circuit keenly. So then you get one problem. So did you observe any problem in that? Did you identify any problem in that? See carefully. Here is the problem. So RL is not connected properly to the ground. RL is disconnected, not properly connected. So in this case, you need to, your value of RL is infinity. Now, at that time, critical inductance became RL by 3 omega. You mentioned it as is infinity by 3 omega. Infinity by 3 omega. It is infinity by 3 omega. So which is infinity. So infinity value of critical inductance. Practically it is not possible. Practically it is not possible. Infinity value of critical inductance. Inductance value infinity. Not possible. Okay. So at that time what we have to do, and we don't know is it connected properly or not. Maybe there is a chance you connected that line in a breadboard, you placed it, but it is not connected properly to that interconnection properly. For that reason we need to connect a high resistance value in parallel with this. So now I'm giving a solution to this. That solution is see this. Now this is the problem. Now I'm giving a solution to that. That solution is a high resistance value connected always as a part of filter, that is RB blader resistor we call it. Now this is the complete inductive filter. In this case, your critical inductance became R L by 3 omega. This is our regular value. If it is not connected, now if it is not connected, the value of this one became RB. See, if RL disconnected, now LC became RB by 3 omega. If RL connected, LC became RL by 3 omega. That's it. Now L naught becomes infinity. We are defining L value something. Now the resistor high resistance value what you are connecting parallel to the capacitor as a part of LC filter is called bladder resistor. RB is high value, high resistance value, high resistance is called bladder resistor. Okay, bladder resistor it is. Is it clear? Now this is your LC filter. The way how we analyze this LC filter, a similar way we analyze the bisection filter. So fourth one is CLC or bisection filter. So first draw the filter section. It is full wave rectifier. Now I'm connecting a C1 capacitor here. This is the LC filter. As usual at output I am connecting a load RL. This is L and C. This is going to be filter. This is bisection filter. You observed one thing. Now this is separated into two parts. Up to here it is a capacitive filter. After that it is a L section filter. Now let us take the equation at this point is V naught. Here we have a triangular wave. Now I am writing the plot for it. So this is the plot for V naught. I am taking the steady state waveform, charging, discharging, charging, discharging, charging, discharging, charging, discharging, like that. And this is the waveform, and its positive peak value is Vm, and its low value is Vm minus V gamma. There is a DC value for this. It is VDC. This is VDC. Its value is Vm minus, this is Vm minus, this is from here to here V gamma. It is V gamma. It is V gamma by 2. So it is Vm minus V gamma by 2. That is the DC value. Okay, that is the waveform at voltage across a capacitor. Now, how we are going to representing that waveform? By using an equation. That is the point here. Okay, now see this. Now the first I am representing this V1 by an expression, by an equation. So therefore VC1 voltage across capacitor is, this is VC1 voltage across capacitor. I am calling it as V0, is represented by DC value of this one minus V gamma by pi into sine 2 omega t minus sine 4 omega t by 2 plus so on. Now finally we need, I am taking only two components. VC1 is VDC minus V gamma by pi into sine 2 omega t, and here VDC means Vm minus V gamma by 2, and V gamma value we know that it is already we derived for in a capacitive filter, that is IDC by 2F0 into C. That is the value of this. Okay, that is V gamma. Now this is the waveform C1, VC1. Here we have VC1. It is applied to the, now it is equal to inductive filter, L section filter, and here we have load RL. It is L, it is C. Okay, it is now inductive filter. Here we have VC1. Similar to that, it is I am taking A, it is G, it is B, it is G, ground. Now same way, XL is much greater than RL and XC is much less than RL. Now the impedance between B to G is approximately XC, and impedance between A to G is approximately XL. XL, that's it. Now so far we know the impedances at every points. Now first I am rating the AC current. This is the DC component and this is the AC component here, VAC. Here is our VAC component, AC component. Now IAC component is VAC by mod A to G. That is, so V gamma by pi into mod into sine 2 omega t by A to G. Between A to G we have XL. Next, this component is flowing this side, current. Now I want to represent that I RMS, I dash RMS. I dash RMS is IAC peak value by root 2. Here we are taking VAC, V dash RMS I want. So this is the IAC component is flowing like this, IAC. Now I am taking I dash RMS. Or you can take VAC also, no problem. Take the voltage at this point and get the RMS value of it. It's not an issue. Both are same. Now IAC peak value is V gamma by pi XL by root 2. By root 2. Now copying this. That is I dash RMS. Just I am going to take that. This is I dash RMS and V dash RMS is I dash RMS into impedance between B to G. That is I dash RMS into impedance between this one is XC mod XC. This is mod XL. Now it is V gamma by pi root 2 into mod XC by mod XL. This is V dash RMS. Now I am substituting V gamma value. V gamma is but V gamma value is V dash IDC by 2F0 into C, or 2F0 into C or F into C, because we are representing this one here by omega, not omega naught. So 2F into C. Therefore IDC by 2FC into 1 by pi root 2 into mod XC by mod XL. This is V dash RMS. Going to copying this. So this is the expression now we have, and with the same time we know that IDC is equals to VDC by RL. Substitute that. Therefore V dash RMS equals to VDC by RL into 1 by 2FC, 2 pi FC I am taking, better to 2 pi FC into 1 by root 2 into mod XC by XL. Mod XC by mod XL. Okay. Now just a minute. So see at 2FC. So V dash RMS is XC, fine. Here we have XC1, that means VC1. So peak value V gamma by this one, okay, fine. And yeah, this is C1, sir, C1, because this is the equation. Here we have a capacitor C1. Is C1. Okay. This is C1. Yeah, now see this. Therefore, V dash RMS by VDC is equals to first mod XC by mod XL is over. Already we taken this one this side. Now 1 by RL into 2 by 2 into 2 pi f C1 into 1 by root 2. Here 2 pi f is omega. 2 omega C1. 1 by 2 omega C1 is XC1. 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 Now it is for V dash RMS by VDC equals to ripple factor is mod XC by mod XL into 1 by RL 1 by RL into 2 by root 2 into XC1 mod XC. This is XC1. Now this one cancelled by root 2 times. Therefore, ripple factor of bisection filter is root 2 into or root 2 by RL into mod XC into XC1 into mod XC by mod XL. The reason to take 2 omega C1 is even harmonics are present in this. The minimum frequency component present in full wave rectifier is 2 omega component. Because of that, this is the ripple factor for bisection filter. So this is the filters with what are the filters we have, that rectifiers with 4 different type of filters. Okay. Now thanks for spending your valuable time with us. Don't forget to use my code VRAO10 during subscription. Hit the bell icon and don't forget to subscribe us. Join our Telegram group for getting latest updates on our upcoming videos. Please give your valuable comments on YouTube. Okay. Now thank you very much. Thanks for spending your valuable time with us. Thank you. Happy learning.